today we will give you a very brief, very fundamental knowledge about PCB designing. Hereafter, it's your responsibility to explore other stuff. So let's jump into our content. I divide our session into mainly three parts. First one is introduction to PCB. Here we discuss basic theory part about PCB settings and what are the available techniques. Likewise, then we will design sample PCB. Under the topic, we will discuss schematic designing and PCB layout designing, and how to export fabrication files and fabrication files, export fabrication files, and how to place order on online site. And after that, we will review a PCB. Actually, it's a 4-layer PCB review. Actually, what I want to give you some advanced tips, since can you all unmute your mute your mics? I'm talking about point 3. We will discussing 4-layer PCB, right? And you can ask question at any time, and if I ask a question, please give some answer, because I would like to have some interactive session. So otherwise this will be getting boring. Okay. So let's jump to our first is introduction to PCB. So before going further, I would like to ask, what is the PCB? Can you give me some answer? Sorry. No one. Just give me some brief answer, what you feel. Actually, there is no very exact explanation. So give me some answer. Okay, I got some answers in chat box. Yeah, I know PCB printed circuit board. It's a short form of PCB short form of printed circuit board. One answer is a board which contains circuit. It's somewhat correct. Okay, let's jump to the answer. Actually, this is an answer I extract from altium.com. Altium is a world most famous and famous PCB design software company. This answer is given by them. Actually, as per them, the PCB is a mechanical structure that contain component and conductors. That's a simple answer. Okay. Okay, now we know what is the PCB, and then question is why we need a PCB. We have a breadboard and Vero board dot board. We can build up circuit on that on top of that, and we can use it. So then why we need a PCB? Can you give some answer? It is okay to put some messages on chat box. Hurry up, guys, otherwise we will our session will be very long. No one. Okay, I jumped to the answers. We need a PCB for mounting components and then make reliable connections among them and save the space. This is answer from my view. There could be many answers. Okay, and also PCB is used to make antennas and matching impedance. Likewise, okay. I hope you all have some electronic basic knowledge. Otherwise, this will be useless for you because this is a somewhat complicated area on electronics. So hope you all are familiar with some electronic stuff, right? And in this session, we are talking about the second type of PCB, not first one. We are actually going to design some professional PCB in professional manner, okay, not homemade one. So keep this in mind. And this is a small video clip, and this shows how to make that second type of PCB in a factory. I mean, I'm talking about this blue color one PCB. Okay. Can you hear the sound? Let me explain some things on the this video. This is shows PCB review. When you submit a PCB design to online site, they review the PCB to what are the mistakes we make on the PCB, or it's and actually this is a necessary phase for calculating the price as well. Okay. They are checking each layer, each component layer and mechanical layers on the PCB. This is how the second layer, two layer PCBs are made. I skipped some part because this is a lengthy video. First they drilled the copper board. In here they are checking each and every electrical traces. The solder mask is actually the PCB color. This is a special test called flying probe test. They are checking each electrical traces with comparing our job file data. I'll stop video here. This video is already available in the YouTube. You can go and see. Yeah. I hope you some get idea about PCB, making of the PCB. Any question up to now? Okay, let's continue. Now I discuss now I'll go to discuss about properties of a PCB. Actually, there are properties more than this, but I'll discuss basic basic properties of a PCB here. So first one is size, and then thickness, and silk screen color, solder mask, layers, component types, and wire types, PCB material, and surface finish types. Okay, the first one is size. Actually, I hope you all know size. What is the size? It is referred to height and width. Okay, then thickness. Thickness is actually thickness of a PCB, but there are some available size. You cannot have any size what you want. There are specific sizes available for thickness. These are defined by the manufacturer. So sometimes these sizes can be thickness sizes can be changed according to the manufacturer's capability, but most manufacturers support following thicknesses. These thicknesses are in millimeter, like 0.2 millimeter, 0.5, and 0.6, 1.6, and 3.2 are the most common one, and 1.6 millimeter is the very most common one. Okay, then we jump into the layer stack up. Layer stack up is how to the way arranging the layers. Actually, they are when we talk about PCB, it's made of several layers, and not just electrical layers. There are also insulation layers as well, and yeah, normally if you talk about our mobile phone PCB or computer PCB, it has usually 16 to 32 layers, but it's but we can maintain same thickness level. If we talk about if you take a 1.6 PCB, 1.6 thickness PCB, you can have 32 layers as well as 2 layers. There are some special layer stack up I will discuss later. Then the component and pad types. Actually, there are mainly two type of component. First one is THT. We also call THD. Means true hole technology or the true hole device, and another one is SMT, or we also call it SMD. T is referred to technology and D is referred to device. Both are same. You can see this below PCB. Here you can see some aluminium silver color pads. We use these pads for mounting SMT or SMD components, and you can see also some through hole, some ring type holes, ring type holes on the PCB. These holes used to mount the THT type components. Here THT through hole component, and these are SMT component. You cannot see such a lengthy LEDs on SMT component. Okay, this is the easiest way to identify them. There are also another properties called it's depend on the component mounting type. The type 1 is one side mounting. I'm talking about this image. You can see there are two components. Those are mounting on top side, and the and both are SMT. Okay, and this image it's also SMT components. Only SMT components are there, and mounting on both top and bottom side, right? And type 2, this is called mixed assembly. In this PCB you can see THT component. There are two THT component on top of the PCB, and in the bottom side there are only one SMT component. Actually you can have many components. This is for example. If we use both SMT and THT together, we call mixed assembly. Actually this is one side mixed assembly, because on one side have one type of component, I mean either THT or SMT, right? Then type 3, it's a mixed two side mixed assembly, because in one side have both type of component, right? This one is THT component and this is a SMT component, and bottom side it's also have some SMT component. Any question up to now? Let me know if you have any question. Otherwise, I will continue further. And this is a wire types. Wire types. Wire is a special technique to use connect more two or more electrical layers together. Okay, let's assume assume this is your PCB, and this is a electrical trace on top of the PCB, and assume this is electrical trace on the bottom side of the PCB. Okay, now if now you want to connect both both layers together. For this reason we use wires. Okay, wires used to connect two or more electrical layers. There are three wire types called THT wire types, blind wire types, and buried wires. Okay, THT wires, actually this is a THT wires because we make a hole through the PCB, so it's a THT wire. And the second one is blind wires. You can only see the one ring on the PCB, but other side, I mean bottom side, there is no ring like in the bottom side there is no ring like this. So these type of wires we call blind wires, and buried wires is this one. You cannot see either top. You cannot see any footprint on the PCB because it is totally internal, right? Grid wires are mostly used in more than 8-layer PCB and blind wires also, right? Then also we can divide PCBs into according to the their material types. There are mainly three type of material. Four type of material. FR4 is most common PCB material, and then flexible and aluminium. And there is another type, copper PCB. It is the means the PCB is built on the copper base, right? These are major category. There are some subcategories as well. I mean FR4, IPC3, IPC2. Likewise, there are so many subcategories as well. Right. Those are the main. I mean, very basic topics to be covered. So, any questions? Because we are next jump into the our second phase, designing a PCB. So it is necessary to understand these concepts. Do you guys have any questions or need any clarification? No one. Okay, let's jump into the our second part of the session. It's about designing a PCB using KiCAD. Here we are using KiCAD software to design a PCB. There are so many softwares available like LTM, ECDA, Proteus, Eagle. Likewise, because we are using KiCAD is most common one, and it's totally free. So you can download it's from KiCAD.org and use it. You can see my screen. When you go to the KiCAD.org, there is a download option, and select your download package according to the OS. Yeah, I select Windows, and you can select any of servers, and then download and install it. Okay. Hope all you are familiar with the installation process, and these are some steps with KiCAD. If you want to design a PCB, there are several steps to be followed. In here, I depicted some steps. First one is we have to identify what is our requirement. Okay. What are the components we need? What are the power supply we are going to use, and what is the output? Likewise, we have to identify our requirement or analyze our requirement. Then designing a schematic and assign footprint, generate netlist. The generating netlist is some necessary step. I mean, unique step to KiCAD. Some of softwares don't need generate netlist, is doing automatically. And the next thing is place component on the PCB and board planning. I will explain each step one by one when doing a example. Just keep this in mind. And then routing, and last one is export fabrication files. Designing schematic in a KiCAD, there are several steps to be followed. Okay, step one is gather reference according to the requirement. It means let's assume you want to add some sensors to your PCB. Then you have to go through the data sheet of the sensor and understand what are the necessary connections to be established, and then you can go to the KiCAD and start new project. And then open. I'll explain this using KiCAD. Otherwise, this will be useless. Okay. And we have to decide which type of component to be components are using. It could be a THT or SMD or mix. And another thing is unit types. We are mostly in PCB area. We are using imperial unit system, means mil. Okay, mil is equal to 0.0254 millimeter, which is you can see, right? And and this table shows component case code. We are called this code for case code. Case code is component size, right? We are mostly using component size 0603. You can see what are the length and width according to the case code. For example, 0603, it's 0.06 length in inches and 0.03 width in inches, right? Here is a size comparison of the resistors, and there are same case code used for capacitors as well. Actually, SMT capacitors. So this is our today goal. We are going to design a PCB that can measure atmospheric temperature and humidity and show it into LCD display. And we are using 12-volt power supply, and also we are using Atmega 328P microcontroller here. We are not using entire Arduino board. We are just take Atmega microcontroller and its necessary component from the Arduino board and those things and sensor. I put it into the single PCB and make power port for 12-volt supply. I already downloaded and installed the KiCAD software, and now I open it and choose a file, new project, and give me some name for project. I'll give some name. Okay. Then you can see your project files as this. The first, there are two. Actually, there are two project files. The first one is PCB file. This is a PCB file, and this is a schematic file. First of all, we designed our electronic schematic on the schematic uh, file. Then we will then we convert it into the PCB. Okay. So double click on the PCB file, and you can see the schematic sheet. The first step is make the adjustment according to your project. I mean, actually, the sheet settings. So there is a button in here. There is a button called setting for paper size. Press it, and then you can see a window like this. Actually, there are some field to enter some details. Those are not necessary things, but those are good practices, right? So we will start with the issue date. The issue date is when the date you are releasing the UI schematic. I uh, I I use the today as the date. Then revision the version. You can see you can enter any version number. I put v 1.0. The title. Uh, uh, Sensor project. You can use any name. It's not company. Using company A, and no need comment 129. And you can adjust the page size. Default is A4 side sheet, and I'll keep it as it is. And landscape orientation, I keep these settings as it is. And yeah, that's enough. See, you can see in the these blocks, it's update, right? The title is sensor project. Here our company name, company A, and revision v 1.0. Here A4 size. Also, we can put some put our company logo here if you want. And this is the our working sheet. Okay. Let's get back into our requirement. Okay, this is this purple color PCB is a SHT31 temperature sensor, and it's also support for humidity as well. And there is a Atmica 328P chip, and there is a power connection, right? Okay, power regulator. Then anyone can tell me what are the necessary components to be used for our project? We don't use entire Arduino board. We just use necessary component from the Arduino board. What are these? Give me some idea. What are the components to be used?
Crystal oscillator.
Yeah, crystal oscillator. What else?
Some I/O pins.
Yeah, I ask what are the components? I/O pins are available in the Mega 328P, no? So what are the component else? We are using at Mega 328P, crystal, and what else? Oscillator, yeah. At Mega 328P, oscillator, voltage regulator, bypass, capacitors. Yes. Okay, I think answers are good enough. Okay, let's design our schematic. First of all, we need a power regulator for our PCB because we are using 12-volt power supply, and but the at Mega 328P and other components working voltage is 5 volts. So first of all, we convert 12 volt into 5 volt. For this purpose, we are using linear regulator. There are several type of linear regulators. So we are going to use AMS 1175 volt. Okay. We are going to use this component. This is the same component you can see in this Arduino board as well. Okay. In the software, there is a toolbox here, and there is a button called add a symbol, or you can press A on your keyboard, and here I click here, then loading the components. Then pop up choose symbol dialog. Now you can search component you need. I enter AMS 117 here. Those are here. Yeah, this is the component what we need here. Okay, AMS 117 5.0. 5.0 is the output voltage, and AMS 117 is the part number. Okay, here I put the when you click OK here, you can move your mouse the place you want, and click on the schematic sheet, and it will hold. And then I need some capacitors for input and output. I search C for capacitor. If you enter C here, you can see some general capacitor symbol here, right? But not footprint is assigned. I'll add some capacitors. Let decide value later. I just paste symbol. And also we need some barrel connectors to connect 12 volt power supply. Let's see. Okay, you can see barrel jack connector. We call these connectors as barrel jack connector. This is the footprint you need, right? And I place it here, and then I'll put some power LED. You can choose footprint here. I'm using 0603 size LED. You can choose one of them. And if you want to rotate the component, first select the component and press R on the keyboard, right? And then it's rotating. And we need some resistor for LED. Press R on the this window, and you will get some general resistor symbols, and rotate the direction you want. And those are the component we need for the power voltage converter unit. Okay, then let's make the let's decide the components values we need. Generally we are using two bypass capacitors to for V in of the what we call regulator, and two output capacitors for V out of the regulator. There are some general values for input and output capacitor. The first one is 0.1 UF, I mean 0.1 microfarad, and then 10 microfarad. And we use same capacitors for output as well, 10 microfarad and then 0.1 microfarad. Then let's select resistor value as 1 kilo ohm. Okay, we select all the values we need. Then you have to make the connection among them. For this, you can see the add a wire button in the toolbox, or you can press W on the keyboard. Here I am using this button and make the connection. And I forgot to mention this in the barrel jack, this pin 1 is the positive pin of the positive terminal of the power supply unit, and pin 2 is the negative terminal of the power supply. The ground is also we can use as a negative terminal, and V in should be connected to the positive terminal of the our power supply unit. Here I am using add a wire button and then draw a wire like this. Then I connect LED to the resistor, and other terminal terminal of the resistor is connected to the ground. Here is ground power port. I want to use a ground label here, and we call these as labels. Okay, this label has some symbol, but sometimes we don't have some symbols for labels. Okay, we call those labels as net label. I will discuss later. If we use same label on different places, it means those terminals are connected to each other, right? Look this, here we are using ground terminal, and here we also use ground terminal to which is connected our number 2 terminal, which means both number 2 and ground here number 2 pin and number 1 pin of the our regulator is connected, right? Here we also use a 5-volt label. I'm using this one. Actually, these are not a component, this is just symbol. Okay, okay, we just done the designing of the our voltage regulator part. Any question up to now? Here we don't use any switches here, but if you want, you can place switch here. Any question? No one? Okay, let's place our microcontroller. We are using Atmega 328P PU version. PU version is this one. Okay, Atmega 328P PU, this one. Okay, AU is SMT1, PU AU, MU, MMH. Those are SMT component, SMT microcontrollers, and PU is the TST1. Here we are using TST1. Then I click OK. Right. Here you can see some pin labels as pin labels. This is the number 8 pin. It is connected to ground port of the microcontroller, and there is 2 pins called external L1, external L2. Those pins are used to connect external oscillator, and number 7 pin is used to supply power for the VCC power for power to the digital part of the IC. microcontroller, and AVCC is the power supply for analog part of the microcontroller, and here ARF is the analog reference voltage for the analog part. If we don't use an AREF, we can place small capacitor like 0.1 microfarad capacitor, like here. So first of all, I connect ground port here. Then I am not using AREF pin, so I'll put another 0.1 capacitor here, and other terminal of the capacitor is connected to the ground. And I'm using a single power supply for both digital and analog part in this PCB. So I connect those pin together and supply and provide a single 5-volt supply. With the Atmega 328P, I'm using two bypass capacitors for the power supply, power input. These are some good practices when you if you are yeah, I put ground terminal, and then we are going to connect extal. Extal mean crystal. Search for crystal and select this symbol and select footprint what you want. Here I am using this one, crystal HC494H. This is the similar crystal, similar footprint for this. Okay. And I put here. Also, I am using 2 load capacitance for the crystal with the value of 22 PF. And a pin of the capacitors connected to the ground. You can ask question at any time, right? Okay, we just complete our basic circuit of the Atmega 328P. Let's connect our sensor. The first we have only one sensor here. It is SHT31 It is a I2C sensor. I hope you all know what is the I2C sensor. I2C is a communication protocol. It use only two wires for communication, and you can connect more sensors on the same bus with different addresses. Okay, this is some good explanation. Here, we are using I2C communication for the sensor. There are two communication pins called SCL and SDA. We can connect many sensors to same I2C bus, but I2C bus with different addresses. Addresses mean each sensors has a different I2C address. You call them by their address. Okay. Here I am using SHT31. In the Arduino, SCL and SDA pins are analog 4 and analog 5. Let's see what are them. I2C pin of Mega. See, this is the Atmega 328P chip, and the you can see this blue color tags. These names SCL and SDA means 27 pin is SDA and 28 pin is SCL. Let's find 27 and 28 pin on Atmega chip. Here, this is our 27 and 28 pins. And what is the 27? 27 is SDA. Here we are using net label for making the connection. We place net label, and here the window will pop up. We use name SCL, actually label as SCL, and place on the 27 pin, and then again we are using label for SDA. SDA is pin 28. Let's verify. Right. Sorry, 27 is SDA and 28 is SCL. I have to swap this. SCL is 28, SDA is 27, right? Okay, we just make connection for I2C. Yeah, SCL is 28. Then we will place our sensor. Our sensor is SHT31. There are few model of the SHT sensors. We are using SHT31. 31 DIS, right? This is a very small sensor. You can see it's about 2.5 by 2.5 millimeter. Address. Let's go through SHT31 datasheet and see what is the address pin. This is the sensor we are going to use. Let's jump into the pin map section. Here, this is the pin assignment. The SDA and SCL pins are used to connect communication wires, I2C wires, and VDD is a power supply voltage input, and VS is connected to the ground. Okay, this is a reference circuit. You can see here, and this RP there you can see two RP resistors. Those are pull-up resistors. They are recommended to use RP as 10 kilo ohm. Okay, and what is the address pin? Address pin input connected to either logic high or low. Do not leave floating. Means you have to connect any of connection. I mean either ground or supply voltage. Let's see some. Here the you can select different I2C address with VDD and VS. If you connect ADD address pin to VSS, your I2C address will be 0x44. This is a hex number. But if you connect this is to VDD, your I2C address will be 0x045. Okay. Let's jump into the software. Let's place some pull-up resistors. Yeah, I mean copy. And place wire between resistor and SCL pin. And we should connect VSS pin to the ground. We can place text anywhere. Then I'll connect ADDR to VDD. And then again I place 5 volt input and also place some bypass capacitor like 0.1 microfarad. Then connect the terminal to the ground, and let's place this label on the sensor. I make copy. Right. So it's done, right? Here what we did was first we made the our power supply unit, then design our microcontroller unit, and then we design our sensor unit. Now what I want, I have to leave a connector for this LCD screen. This LCD screen is also using I2C communication, so I'll place 4-pin connector for the LCD, 2 pins for I2C communication, I mean SDA and SCL pin, and other 2 pins for 5 volt and ground. Let's find out some connectors here. There are so many footprint. Please use connectors with 2.5 millimeter. I'm using this connector, this footprint for the connector, and place OK. Press R for rotate. One pin is connected to the ground. Another pin is connected to the 5 volt, and rest 2 pin are connected to the SCL and SDA. Let's see them. Okay, we just complete our schematic design. Okay, so next step is assign footprint for the component. For that, I use this tool, run footprint assignment tool. Yeah, first of all, we have to use designator tool. Means you can see C question mark, C question mark, again U question mark, J question mark. We don't need such a question mark. We need C1, 2, C3, U1, J1, like numbers. So first of all, we need to use designators generator tool. We call this number as designators. So click here, and you can see annotate annotate window. In here you can select order x position or y position, and there are so many settings as well. I keep those things as it is and press annotate button and then close. See, you can see C1, C2, C6 and U1, all footprint, all designators are filled with some numbers, right? Then here click run footprint assignment tool. Here you can see we don't assign any footprint for any of the capacitor and any of the resistor, but LED we assign for LED we assigned footprint and connectors and some other stuffs. We already assigned a footprint. So here we are using same case code for capacitors. So I select all and find some capacitors footprint. Let's see. You can see capacitor. You can type capacitor here, and in this area you can see what are the available capacitors for available footprints for capacitors. I select this one. I'm using a 0603. You can see two footprint for 0603, both are same. I just assign this one, right? You can see all footprint are assigned, and I will do same thing for R2 and for our resistors. I am searching for resistor. Here I would like to use 0603 for resistors as well, so I click this one. Okay, now we assign footprint for all the components in our project, so then click OK. Yeah, we just complete our basic things in the schematics. Sorry, all the things in this schematic. Let's move to the our PCB file. Before that, we have to update the PCB from the schematic. So so that go to tool menu and update PCB from schematic. There are some errors. J1 pad MP not found in connector barrel jack. Let's I think there is no issue because the connector barrel connector is also here, already here. So this is our PCB file, and you can see a 3D view. Okay, these are our set of components. In this side you can see all the layers in the PCB project. There are several layers to consider. The first two is those are copper layer. This is in default. The KiCAD is prepared for two-layer PCB design. We can change, but by default there are two layers for electrical connections. F.cu is front copper layer, and B.cu is back copper layer. Okay, and there is another layer called edge.cut layer. This layer is used to define your board shape. You can use these tools to define board shapes, and here F1 F.silk screen is front silk screen layer, and B.silk screen is bottom silk screen layer. And there are some additional layers for user settings. We don't use those layers here. Okay, let's first of all we define let's define our board shape. I use select edge cut layer. You can see there is a small arrowhead here, which means it's indicate activated layer. And here I click on the edge cut layer. Then I select draw a line tool on the toolbox. Then I draw a PCB. Here I am defining some square shape. Right. Right, this is our PCB, and the first phase in the PCB PCB tool is done. Then next let's move to the settings in the PCB tool. Here file, for that you can use file, board setup. This is the board setup window. If you don't use these extra layers, please untick. And don't remove others, those are necessary. Here you can define the layer stack, what you want. I'm go with default settings, and here you can see copper layers. I am using 2 layers. You can have other layer settings. Seems like this KiCAD is not supporting for one layer designing, so always there is even numbers. Then text and graphics, we don't change anything here. Then the other thing is design rule. Under the design rule section, you can find predefined sizes. For trace sizes, there is a tracks, we also call traces, so electrical current path, whatever. We can have some predefined sizes for tracks. We mainly use tracks, so the traces for signal and for power path. For signal, most of the times very thin or narrow traces are enough, but for the power traces we have to use much larger power traces. So here I put some width, the width is in the millimeter. I put 0.8 millimeter width tracks, and I use general wire size as 0.5 and hole size as 0.3, and then press OK. You can see track sizes here and wire sizes here, and you can change grid size. Now I'm going to place components in the relevant places. First I place our barrel connector, then C1 or C2, you can use R for change the rotation. Here C1, here I disable this FFab layer, and that's C2 or C2 here. You can use scroll wheel and control button in the left your keyboard to zoom in and zoom out. Next to capacitors, I put or regulator. Yeah, I think this is place for regulator. Right, then what are the capacitors for out? Power out C6 and C7. Likewise, Then place our LED. What is the resistor for LED is R1. That's the R1. Yeah, R1 and LED. Here D1 is our LED. Right. We just complete our power supply section. Then we are going to place our microcontroller into orientation right here. Then place our capacitor, also oscillator. And with the oscillator we using two load capacitors, C8 and C9. Right. Then again bypass capacitors for power input, C3 and C5. By C3 and C5. Yeah. Place them close to the our power pin as possible. Right. And what are the left component? We just see. We have to put our C4 capacitor. C4. And then our sensor. These are the pull-up resistors of the I2C line. Right. And here, and the C10 for bypass capacitor for our sensor. I just put it here, and I place our I2C connector for the LCDs here. Yeah, placing the we just complete our component placement phase. See our 3D. Here you can see our 3D view. Right. Let's move to the around the board. I think we have to define some arrow track for an arrow track size for the this component, this sensor, because these pads are very small. So I think I think we need some small tracks. I'm going to use 0.2 tracks for our sensor, and 0.8 track for power bar. First of all, I would like to routing our power bar. You can use this tool, route tracks, or press the key, X on the keyboard or start routing. And 5-volt connection for And here I select 0.2 tracks for our sensor. Yeah, I want to connect this SDA pin on the ATmega 328 and SDA pin on the our sensor, but there is looks like there is no way to direct connection. We can route like this, but the trace length will be very lengthy. So, but we won't make it as short as possible. So I would like to use wire here. For wire, you can select wire type, wire size what you want. I just define one wire type. Select it and place uh, wire tool on the toolbox and place it here. Right. Then press escape button. Then click bottom layer. Here we are use bottom layer to continue rest. Right. So it's easy. Then shift to okay. We just complete our sensor. Right. And again, I select bottom layer for making connection between our controller and I2C connector. Right. Okay, we just complete our routing process, but we left ground connection. We are using copper zone instead of tracks only PCB. Let's use copper zone. Here you can see add field zone under the place menu. Once you select field zone and click the start point of the PCB, I click here, and then this window will be pop up. You can select both layer, and we are used this copper zone for ground connection. So I select this layer, this net ground connection net, and there are so many settings. You can keep it as it is, and then press OK, right? Then you can draw a ground. Then you can draw zone. Then double click at the endpoint, right? Here you can see this with the copper zone, the whole ground connection now made. But here you can see this small area do not connect with any other ground area. So to avoid this, we are using via for this. Yeah. You can see that you can see this line will be disappear. Right? Yeah, our PCB is just complete. So next thing is we have to export the fabrication data for PCB manufacturer. Before that, we have to make sure the all connection now done. For this we can use design rule check option. For the DRC, check this button. There are several options. Yeah, let's run DRC. See any issue. Yeah, there is no any issue. You can see violation 0, unconnected items are 0. Schematic parity, we don't run it. So there is no any unconnected thing or any warnings or violation. So our design is complete. And this is ready to fabricate. Let's see our 3D view. Yeah, here you can see. One thing I forgot to mention, you can use names for pins of the connector. For this, you can select F-Silk screen layer, and then select add to text item. Here you can place a text. What I want to do is I want to label each pin on the connector. Yeah, I make put the name TND SCL SDA and 5. Now any person can understand what are the pin connection and rotate and place it close to the connector, right? Now anybody can understand what is this. Ignore these colors. When you print the PCB, you can select what are the colors you need. Okay, we just complete our PCB and please save. And for fabrication, for PCB printing process, go to file menu and fabrication output and JAB files and select your component layer, application layers. These are good, sir. Yeah, these default settings are correct. Then plot format, select JAB and output directory. Select the place where you want to save the files. I make project output folder and output, yeah, that's it, and select the folder and please uncheck this X2 and other settings are correct. Then plot and then generate drill files. Select here JAB format and absolute, drill origin absolute, and drill units inches is correct, and then generate drill file and generate map file. Okay, and close the window. Then go to the project file here. Inside the project output folder, you can find those JAB files. Then select all and make a zip file. Workshop. Today I'm going to use JLC PCB for fabrication. Go to the JLC PCB and sign in to your account or sign up if you don't have. And here add a JAB file button. Select your JAB files here. Project output, this one. If you export JAB file correctly, you can see preview of your PCB here. If there is no preview here, there could be some error issues. Okay, then here you can select material you want. FR4 is the most general one. Aluminium PCB, aluminium material is generally used for LED, high power LED PCBs. So here we are using FR4. and we are using 2 layer. And if your zip file is correct, the JLC PCB is automatically understand what are the size of the PCB. Then select your quantity what you want, and different design, select one. PCB thickness 1.6. Here you can use any color. Those are same price but take different lead times. I'm using green. Then silk screen. Silk screen is a text color on your PCB. Here text color is in the preview it is black, but the JLC PCB there don't have black color option, only white option. And the surface finish HSL is enough. If you are making a PCB for overseas market like Europe, American, or Australia, New Zealand, you have to use lead free one. There is 2 options for lead free PCBs, lead free HSL and NH. You can both you can use for export product, and keep these settings as it is, and make sure flying probe test is fully tested. Okay, and then here you can see calculated price. Right, then press save to cart. Once you press save to cart, you can go to your cart. Here you can see this is our project, and price is $2. And then go to secure checkout. And select the shipping address, billing information same as shipping address. You can choose one of the option for shipping, DHL, UPS, FedEx, and also e-packet option. You can see select e-packet option for budget project. You can see the shipping price is $6.9. For others, FedEx it is 23.28, ups 76.47, and DHL it's is 59.37. So for budget project, e-packet is would be the best option. And then continue. Submit order, use this pay directly settings, and continue. Then select a payment option, and here you can use PayPal or credit card option, and then enter your credit card information or PayPal and press the pay button. Then once the production is complete, it will be received to you. So that's all about the PCB designing and ordering process. So any question? Because we next jump into the PCB review part with advanced tips. So any question? No issue. Is it? Can I jump into the next section? uh, okay. Here we are consider some issues related to the PCB design and signal integrity. When we talk about signal integrity, there are signal integrity due to mainly four for four reasons. First one is crosstalk and the reflection and attenuation and ringing. So what is the crosstalk and reflection? There are some good YouTube video I just done.
You get displacement current going to the quiet line that builds up some charge.
Have you ever thought about what makes plastic parts so durable and safe?
Makes a voltage. Here's a victim.
This is the crosstalk effect. Actually, this is a if you have two parallel paths which is very close to each other, and the one of the signal trace is working on very high frequency, then it is supposed to induce some voltage on the other traces. This is the basic, very basic idea about the crosstalk. I will share this link to the I will share this presentation to the WhatsApp group, then you can have a look it. So this will be a problem in very high frequency circuits such as 500 megahertz circuits and or above circuits. So due to this fake signals, your system will be crashes. So I left you to watch the video, and the other thing is reflection.
To send an electrical signal, we need two wires.
This is a good video for understanding reflection effect.
Conductors are by definition a capacitor. This means that each section of our transmission line has some capacitance. And since a loop of wire is by definition an inductor, each section of our line also has some inductance. Suppose we close a switch, applying a constant DC voltage across our two wires. This capacitance and inductance is what prevents the signal.
This video shows every transmission line or the wire has self-inductance and capacitor. We don't put any capacitors and inductors externally. There are always self-inductance and capacitors.
From traveling instantaneously. Therefore, we can never eliminate this capacitance and inductance completely, because this would then violate Einstein's theory of relativity, which states that information can never travel faster than the speed of light. These capacitors and inductors shown are not components that we deliberately add to a circuit, but are an inherent part of all wires that carry electrical signals. When electric circuits appear to behave in unpredictable ways that seem to violate the laws of physics, this is often due to the capacitance and the inductance of the wires. In this instance, for example, the signal keeps bouncing back and forth between the beginning and the end of this transmission line. With nothing connected to the end of the line, the voltage at the end of the transmission line reaches double the value of the DC input voltage from the battery, and the signal is then reflected back. Reflections can also occur at the connection between two transmission lines which have different amounts of capacitance and inductance, in which case only a portion of the signal's energy is transmitted to the next line, and the rest of the energy is reflected back. Suppose we connect a short circuit at the end of a transmission line. What will happen when this signal reaches this short circuit? As always, the speed with which a signal travels depends on the capacitance and inductance of each section of the wire. When the signal reaches the short circuit, the signal is reflected, but with the voltage flipped upside down. If the impedance at the end of the line is too low, it will behave like a short circuit. And if the impedance is too high, it will behave like an open circuit, both of which cause reflections. But if we place just the right amount of impedance at the end of the line for the amount of capacitance and inductance in each section of the line, then the amount of reflection can be minimized. Reducing reflections is desirable, as reflections can significantly interfere.
Hope you all get some idea about reflection. So if reflection is happen, if you send some signal to the antenna or some receiver, it will get back to the transmitter. So we have to avoid the reflection effect, right? So next thing is attenuation. Attenuation is loss of energy. I hope you all know about the attenuation. This is somewhat related to the filters as well. The another thing is ringing. So ringing is the in the in this oscilloscope image, you can see the yellow color one. It's look like a wave, but what we expected is the red color line. Due to reflection effect, ringing effect, actual signal will be the yellow color one. You can see there is a huge oscillation on the change at the changing or the changing edge. So this is lead to some malfunction of your circuit. So we have to avoid these things. So how to improve signal integrity? How to improve means how to avoid those problem in your PCB. Actually, we can use some techniques and terms of rule for this. The first one is reference plane. Always have a ground plane adjacent to a signal plane. Important for control impedance and return current path. Actually, this is also a reference plane. We are using a zone here. This is it is also reference plane, but we don't have any separate plane for the reference plane or the ground plane, and the separate plane for the signal. Here we use same layer for reference plane and signals. This is ideal case for PCBs that have more than 4-layer PCBs. And the next thing is use a proper layer stack up. There are some layer stack up available for some available some layer stack up that are unique to the manufacturers. So all the stack up details are available in their websites. You can have a look at. This image I extract from PCBway.com. As per them, their support for 4-layer stack up. 5 stack ups. No, actually, this is a two type of 4-layer stack up. The first one is you can see there are same gap for both electrical layers, and these four are in between the internal layers. There are huge gap, and between internal layer and outer layer there are small gaps. So you can have when you defining the layer on your PCB, you can pick one of them. The most common one is this one. Okay, for this is first layer, second layer, and for 3 and 4th layer. We use first layer for high-speed signals like USB interfaces and HDMI display ports and eMMC RAM slots. Like we use first signal for first layer for routing high-speed traces. Then we use ground connection, and then we are using power plane for 3rd layer, and the last layer, bottom layer, is used to connect low frequency connection, like on of the some GPIOs and low speed protocol like I2C, UART. Likewise, it's those are comparable to the low to the high speed traces. This is the most common layer stack up, and Even if you're using 4 layer, you can please use this this one, right? And this is I extract from again PCB way. You can see how the PCB layers are arranged. The very first layer is top overlay. Here we are talking about just copper layers, but there are some additional layers as well. The top layer is for signal. You can see the top copper layer. The very first layer is top overlay, then top solder, then top copper layer and dielectric layer, and again signal, dielectric. Likewise, there are so many layers. Some manufacturers are allowed to use layer stack up with UR settings. Okay, you can contact manufacturer and ask them to change this gap, change this gap to this one, and use this material as this dielectric layer. Likewise, you can ask and contact ask from them to make custom PCBs. And there is control impedance traces. This is related to your our reflection effect. If we are using especially antenna interfaces, we are mostly control track impedance to 15 ohms, and according to the our layer stack up and layer copper width, copper height and surface finish type, the width of the track will be changed. So you can calculate using this tool. This is very easy tools for calculating control impedance. Here select impedance and trace space. Mostly we are using 50 ohms control impedance for antenna interfaces. So put it as 50 ohms, and signal ended, antennas are signal ended, and then select type inner or outer layer. We are using outer layer, and then calculate. Here you can see recommended trace width for this layer stack up, and this trace width for this layer stack up. You can select one of the stack up first and adjust your antenna trace width according to the your layer stack up, right? Let's assume if we are going to use USB 3.0 interface, it's mostly use 90 ohm. So put 90 ohm, and USB interfaces are mostly differential types. Actually, not mostly, it is differential type. And trace space, select 4. Here you can see what you can see the required trace width for 90 ohm impedance, right? And the when we are routing high-speed traces like USB traces and the eMMC RAM chips, like and then HDMI ports, then Ethernet port. Likewise, you have to keep you have to separate those traces at least 3 times of their dielectric layers. Means assume this dielectric layer 1, assume this thickness is 1.22 millimeters. So 3 times of this layer is this height is 3.66 millimeter. So if you are routing differential pairs on the first layer, you have to keep at least 0.366 gap between this differential pair interface, right? And the next one is bias. When you are placing a bias on the PCB, try to avoid bias in signal path. It means let's assume you are routing a antenna interface, so don't use bias to connect bottom layer and or internal layer or whatever. Just use single layer for entire trace. But if you want to change layer, just assume USB path, you have to put some wires closely to your signal layer that is connected to the ground layer. Okay, we call this techniques guiding the return current path, and it will improve return path by stitching ground plane with wires. Then next thing is split ground plane. Assume you are using a special analog receiver and digital processor. So if you want to connect signal line to the from analog chip and digital processor, we have to use some cut between ground plane in the ground plane, and then you want to connect your signal path, and you want to connect analog circuit and digital circuit. You have to use traces like this, okay, not like this. This is also helps to avoid loops area in your PCB. The next thing is power supply selection. Let's assume this PCB. You are using analog chip and your digital chip here. But for this case, the ideal solution is use two separate power supply for digital section and analog section. This image shows it. But in practical scenario, we don't use two power supply for analog section and digital section, because it is it is a costly option. So we don't use such option in normal case. For this reason, the most practical solution is this. We use single power supply for digital power input, and we use the same power supply with ferrite bead. This is a ferrite bead for analog power supply. So this is the cheap option for cheap option for mixed signal operations, right? You can check this link about for more information, and I'll see some PCB with 4 layer. Now we are talking about this PCB. Right, this is a carrier board for Raspberry Pi module, compute module 4, and this is the PCB design. Here, see, let's see some stuff on the PCB. Okay, you can see these. Actually, these there are two HDMI port. You can see there are some spiral on the PCB traces. So what is this is what we call this technique is length matching, or we call length tuning. So you can see those are name. Consider these two traces. The first one is HDMI 1 D2 N. N mean negative. The next one is HDMI 1 D2 positive. The same signal but differential. Means this is N. This is negative. This is positive. So for this reason, we call this signal pair as differential pairs. We have to use same length of the same length for both traces. So as you can see, this trace is little bit lengthy than this. So make the so adjust the length. We use the extra spiral on the this trace. I mean the shorter trace. So you can match the length there. And the next thing is you can see here there are small wires on at the end at the edge of the this set of traces. This is a technique called return current path guiding. Here just before we discuss, here this one, and you can see the more wider current traces for 12-volt power supply, and here they separate the power supply. This is a power supply section, and this is digital processing section, and they make the cut on the ground plane. Here you can see, and this is the top layer. Here this is the second layer. The second layer is also connected to the ground, and this is third layer. There in this board, the third layer is also connected to the ground layer, and fourth layer there is again signal layer, and also ground layer. Ground plane is also connected to the bottom layer. Here you can see the 3.3 voltage path on the bottom layer. Both internal layers are directly connected to the ground plane, and there is no any other signal layers on the ground plane. they are using this layer stack up option for this PCB, right?